Hi, I'm Mike McCarthy. I'm a professor of mechanical engineering here at UCI School of Engineering. I'm pleased to introduce Robert Smitty Smith, who's going to begin a series of lectures on race car engineering.
Thank you, Professor, and I'm Smitty to everyone, and I'll be taking you through a series of hands-on demonstrations on the workings of race cars to get you guys and girls all jump-started in your projects. So we're going to keep it light, we're going to keep it fun, we're going to keep it informative, so let's get busy and build that car.
This is a series of about 20 lectures, and it's the start of more to come. I hope you enjoy this series. Thank you very much.
See you in the shop. Hello, I'm Robert Smitty Smith here at the University of California in Irvine in the School of Mechanical Engineering, and I'm an advisor for the FSAE Senior Project. Have been doing that for a number of years, and so this little video is to lay out some basic parameters that startup FSAE teams could find useful, because I always get this question, well, we got to design a car and a chassis and we don't know what number to make that or what dimension to put there or anything because we've never done it before. Of course you haven't done it before, you're students. So let's see if we can lay out some basic considerations for doing one of these FSA project cars, or if you have a generic race car that you're doing on your own. So let's set down that little model. So here I prepared a list of 18 starting considerations. Now, the first thing that should be looked at when starting a car designed from scratch is the thing that mechanical engineers deal with the most, and that is the tire contact patch. All right, now your contact patch and dealing with it and optimizing it means you're dealing with tires. So the first thing you deal with is select your tire you'll be using. Don't think about engine, don't think about anything else. Think about the tire you're going to be using. And the most important initial thing is the tire diameter. Now in FSAE you can use a tire as small as 8 inches in diameter. That's larger than a go-kart. They don't want you using go-kart wheels. You can use 8s, 10s, 12s, 13s, 14s, 15s. They don't really care on the upside, they care on the small side. The most common size is a 13. 13, you have a very large selection of wheels. You have a very large selection of racing tires, rain tires, that sort of thing. There is a problem with the 13 in FSAE, and that is the cars aren't going fast enough and aren't heavy enough to properly heat them to their optimum temperature. Plus the fact, if you have a selection of 10-inch, the 10-inch tire runs warmer. Why? Because its circumference is less, and so the heating cycle, which takes place at ground level when the tire rotates around, comes around in a shorter time window per mile travel. So a 10-inch tire will run warmer than a 13-inch tire, which means it will be up closer to its best operating temperature. It also is lighter, and weight is a big consideration on these cars. My personal preference, if I was starting from scratch and had the budget, I would go with a 10-inch tire. Then I would try, especially if I could get a 10-inch racing tire in the proper soft compound, at the same width I could get a 13-inch tire. If I could do that, I would definitely go with a 10-inch tire. Well, what's the downside? If there's an upside, there's always a downside. The downside is the smaller inside of the wheel makes fitting brakes, uprights, steering linkages much more difficult. The packaging of the steering and braking system is more difficult. Can be done, of course, but it's easier in a 13. So tires, figure out the diameter. Then figure out from that diameter which tire you're going to use, which will give you the height. It's important to know the height because you need to know the radius from the pivot of the wheel to the ground, that radius length, because that's going to determine some more geometry down the road. Compound. Like I said, because temperatures aren't usually very high on these tires, you want the softest compound available, period. Width, as wide as you can get. Once you figure out what the width is that you can get with the proper compound, with the proper height, with the proper diameter, that will determine the wheel. Because the wheel has to be wide enough to fit the bloody tire. You can't put a tire this wide on a rim that's this wide. Okay, so select the tire, and then that's going to start a cascade which is going to dribble down. Now, continuing on, the first geometry setting we need for the tire is camber. We get that as per the tire manufacturer will have a number of degrees which his racing tire will work best. That is your target camber setting. However, you have to design in an extra 1 1/2 degrees of adjustment minimum. Why? Because this is a dynamic under maximum load camber angle. Happens to be 1/2 degree for the tires we run here, but we need more than that because there's going to be compliance in the chassis, in the suspension arms, in the pivots with the bolts and the bushings. So we got to have more in order to have the proper amount under max load. Okay, so there we go. 1, 2, 3. The next thing we need to decide upon is wheelbase, and it's pretty simple in FSAE. 60 inches is the minimum allowed by the rules. Short wheelbase equals nimble. The car will be operating in autocross conditions which demand the utmost in nimbleness. You're not going to Bonneville. You're not going to Indianapolis. You're not even going 200 miles an hour to drag strip in a straight line. So you don't need a long wheelbase for high-speed stability because the speeds are so low. What you need is nimble. So 60 inches or slightly over is the best wheelbase dimension. Now, track. That's the width of the wheel. So here's something that a lot of people just don't think about because they haven't done it before. And then what would be the track setting? If we know the wheelbase, we can automatically know the track. If we know the track, we automatically know the wheelbase. All right. If you want nimble, the most nimble vehicle you'll ever see on an autocross track is a shifter cart, a go-kart. And if you look at go-karts, you will find they have an aspect ratio of about 4 to 5. They're about 5 parts long, 4 parts wide. So the track needs to be 75 to 80% of the wheelbase. So whatever the wheelbase is, take 75 to 80% of it. That will give you a great starting point for your track dimension. Now, once you have established a track dimension, that's the center of the wheels to the center of the wheels, as up here, then guess what? Then you can start looking at A-arm lengths. A-arm lengths, that's going to be your mechanical connection from your pivot on the chassis proper out to the upright, which is supporting the wheel. So, here's the general rule of thumb on that. The longer the lower A-arm, the easier it is to get rising camber geometry that you'll need when the car banks over, rolls over in the turn slightly, and you want to keep that contact patch flat on the ground. You have to have something called rising camber. So a long lower A-arm makes that easier to achieve. The upper A-arm should be between 50 to 80% of the lower A-arm. The reason for that is something we'll get into in a little bit called rolled center. If it's outside these parameters, you probably aren't going to be able to create a geometry that's suitable, or as suitable as you would like to have. Okay, so we got A-arm lengths, we got track. Now, number 6, vertical center of gravity. We need to know the maximum it can be. As per the 60-degree tilt test, this is a picture of this is in the book. These vehicles will be tilted up from horizontal to 60 degrees to simulate 1.5 G cornering load. Now, in order to do that, the vertical center of gravity of the car has to be below a certain level and has to be relatively centered in the car. If it's above that, the car, when it goes up on the tilt table, is going to roll off the tilt table. All right, 60-degree tilt test. Now, if the car is going to be tilted 60 degrees, we can find the maximum height our center of gravity can be as long as we know the track of the vehicle, the width of the tires, which we've already decided upon. And guess what? If it's going to be tilted up 60 degrees, that means we go to outside of the tires on each side, ground level line, come up 30-degree angle, where they cross. That's the highest the center of gravity can be allowed to be, or else it will not pass the tilt test. This distance here is your maximum for vertical center of gravity. Very simple to lay out and calculate, figure out. Nothing to it. Now, once you get that dimension, then you can go to number 7, roll center heights. Roll center heights, you're going to have a certain geometry described by the suspension. And that means that the chassis proper is going to roll around a center. That's rolled center height. See how easy engineering is? Now, here's the basic rule of thumb on that I subscribe to. Others do not subscribe to it. They prefer to put the roll center height underground. I think that causes more problems than it cures. But here's my crew chief rule of thumb. The rear roll height should be at a maximum now of 30% of the vertical center of gravity height in the rear. In the front, it should be no higher than 15% of the vertical center of gravity height. That vertical center of gravity height is the same for the front and rear, but you want the front roll center lower than the rear. This is the front of the vehicle. You want the back end up. The reason for that is the car will roll over and take a set in a corner better if the back end roll center is a little higher than the front. If you can get it down on the ground level without compromising two other things, great. The reason you don't want a high roll center is something called jacking effect. Jacking effect is sort of like a pole vault. If the center of gravity of a car is high, as the car rolls over, the car tends to rise on the springs. If the center of gravity is low, the roll center is low, then very little force goes into a rising component torque that causes the car to rise. Because as the car rises, the center of gravity rises, and then things tend to go downhill, and the center of gravity could go up and get outside the accepted envelope and could get up on two wheels or even roll over on its side if you had enough jacking effect. So jacking effect should be minimized. All right, just that simple. Steering geometry, number 8. Select the basic steering geometry for the car between Ackerman, now there's full Ackerman, and less than full Ackerman, and even reverse Ackerman, or parallel. I say for autocross, Ackerman, Ackerman, Ackerman. If you can't get full Ackerman, then slightly less than full Ackerman is okay. I find that it works superior than any of the others. All right. Number 9, kingpin inclination. Kingpin inclination is for returns the wheels to straight ahead when you let go of the steering wheel. It's for straight line stability. You have to have some. I would say a minimum of 5 degrees to a maximum of 15 degrees. Now, I'm not going to just give you a number and say do that. You have to make some selections based on other things, because this folds into other geometries, and when you change one, you change the other. If you do one thing over here, then something else has to happen over there. You still have to do your due diligence, do the research, figure out what kingpin inclination is from the books, and work on it. Now, kingpin inclination leads us directly into scrub radius. Scrub radius, needs to be, I think, on these size vehicles between a positive 3 inches and a negative 1 inch. There's illustrations in the book that will illustrate scrub radius. The more positive the scrub radius, the more feel that the car has, but the greater the steering effort. You can reduce the steering effort by bringing it down to 0, but that takes away feel. However, if you leave it up here where you have a lot of feel, that causes other problems. Changes in track, changes in wheelbase, changes in the stability of the wheels, especially under heavy braking. Okay, scrub radius. This is just a basic generic range in there. If you select anything in there, the car will drive. Okay, caster. The rule of thumb about caster is never ever let it go below 1.5 degrees at the dynamic maximum load on the vehicle. That's when the vehicle is braking and the back end is coming up and the front end is squatting. You never let it go to 0, or goodness sakes, do not. It's horrible if it goes negative. If it goes negative, you're going to get violent shimmy in the front wheels. It can be really severe. Dynamically, 1.5 degrees under worst case conditions. 5 to 7 degrees of caster would be what I'd consider mid-range, and up to 15 degrees would be toward the high end of a caster setting. Okay, toe, simple, 1/8 inch, front and rear wheels to start. Adjust from there. Suspension travel. In FSAE, you're required by the rule book to have 2 inches minimum. Okay, so you got to have 2 inches, your actual suspension travel to be determined. 3 inches, not a bad idea. Trying to get really close to 2 inches, depending on the courses, they do have dips, they do have unevenness. You do need suspension travel so that the wheels can stay in contact with the course at all times. Turning radius. This is the minimum turning radius of the car. This is where you should go again to the rule book. Should lay out in the rule book what the tightest corners will be in radius. Well, guess what? The car needs to turn tighter than the tightest corner. Why? Because if the car starts understeering, you've got to crank in more steering angle. So if you've got a steering limit right here that just matches the turn radius of the tightest corner, you're not going to be able to turn past it and then come back for adjustment. So I'd say about 2/3 required for the tightest corner. It should go past that. Okay, steering motion, lock to lock. Steering wheel, all the way this way, all the way this way. Don't have more than a 1 1/4 turns. Not for autocross, 1 to 1 1/4. Why? Because if the driver is having to shuffle the wheel around, he's going to have slower lap times, period. He needs to be able to. Autocross, especially on these cars, is absolutely thrust, cut, push, slam, jam. It's slam and jam. There's no real finesse to it. Okay. Was our steering lock to lock. Now, number 16, bump steer. Bump steer is error in the steering system caused by suspension motion. You naturally want it to be 0. That's the theoretical ideal. It is very, very rarely achieved. But you should measure that after the suspension is completed. This is sort of your grade. If it's very, very low, you did a great job. If the wheel, as it hits the bump, suddenly points over away from the intended direction of travel, well, that's not good. That means the car is going to steer itself when it hits an undulation in the track. Suspension linkage ratio. For FSAE cars, you're always going for lighter weight, lighter weight. One of the things you get lighter weight, you use small suspension springs, you use small shock absorbers. In order to do that, you need to have a favorable linkage ratio. A very good one, if you can, is 2 inches of spring travel for 1 inch of wheel travel. If you can get that, you can use very small springs, very small shocks. If it goes the other way, 1 inch of spring travel for 2 inches of wheel travel, you're going to have to use a truck spring. Okay? Now, 18, chassis rigidity. This is what I think is a good chassis for a tube chassis. Chassis rigidity. Torsional rigidity, if it's 2,000 foot-pounds per degree, I think that's good. It's not as good as possible, but it is very, very good for a student design car to have 2,000 foot-pounds per degree of chassis rigidity. In beam loading, at least 4 times that. I like to see about 8,000 pounds, 1 inch deflection in the middle of the chassis. If you've got that, you've got a chassis plenty stiff enough to fly around one of these tracks. Why? Because there's only so much load that can come from these tires. Okay, so there you go. 1 through 18 starting considerations. Start with your tires, move toward the driver. And now, finally got around to the driver. Now, I've served as a judge at an FSC, a design judge at FSC design events. And there's one thing that I and others have noticed, and that is how little, it's pitiful the amount of consideration that goes in to the driver ergonomics. That always seems to be one place that could really, really stand improvement on these cars. And I must admit here at UCI, where the students do design the cars, I just stand back and close my eyes and hope for the best sometimes. We have our last year's 2011 car, which actually won one of the events outright at the FSA event in Fontana. The drivers can't see out of it very well. The first thing I would want to consider if I was a driver is, can I see out of the car? Can you see? Put that on the top of your list. Now, the other thing is, can the driver see the gauges? I actually got in that car and drove it, and I can see the tachometer, which is the only real instrument in the car, from about 7,000 to about 8,000, but I can't see it any other time. Why? Because the steering wheel's in the way. Okay, I guess I only need to see it when it's right there. So things like that, drivers being able to actually drive and manage the car are important. And where are the driver's knees going to go? Are they going to be banged up inside the bottom of the instrument panel? Or elbows. The car has horrible elbow rooms. I'm using our car and I'm picking it apart to show you that we're guilty of this as anyone. The primary designer on the car, when I asked him about these things, he said, well, drivers aren't supposed to be comfortable. They're supposed to suffer. I say, okay, well, I don't mind suffering for a lap, but that endurance event went on for half an hour. If you expect peak performance, the driver needs to be properly supported, needs to be able to see, needs to be able to steer the car. The other thing is a lot of teams like to use these little tiny coffee can lid size steering wheels like this, and they've got enough geometry and they got big slicks. One driver came out of the endurance event and said, if it had gone one more lap, my arms would have fallen off. Why? Because the steering level is so bloody high. Look at these things. This is all part of the development process when you're testing the car, is to make the darn thing work for the driver. Simple little things like an adjustable heel stop so the driver's foot doesn't slide around in there when he's modulating the gas can drop a second or two off a lap. Just nothing but a little heel stop. Little things like that. So look at your driver's ergonomics. This is probably the most neglected thing in FSAE design. All right, that's it. That should give you some starting points. Go out there and build a car.